Hello friends, I welcome you in lecture number 21 on complex differentiation. In previous lecture we have seen about exponential function of complex variable, and now we are familiar with the definition of complex exponential function. Now we know that if z is a complex variable given by x plus iy, then complex exponential function is denoted by e raised to z and is defined as e raised to z equal to e raised to x times cos y plus I sin y. And in this lecture we are going to discuss one more property of this complex exponential function. We have proved this property of this exponential function in lecture number 20. In lecture number 20 we have shown that e raised to z is analytic everywhere in the complex plane, and therefore e raised to z is entire function. Today we are going to prove another property of complex exponential function, which is similar to the property of real exponential function. We know that if we have a real exponential function e raised to x, then e raised to x1 plus x2 is equal to e raised to x1 times e raised to x2. So in complex analysis also this property, similar property holds, that is complex exponential function also satisfies the property similar to real exponential function. So we try to prove this property e raised to z1 plus z2 is equal to e raised to z1 times e raised to z2. For that we consider two arbitrary complex variables. Say z1 is given by x1 plus I times y1 and z2 is given by x2 plus I times y2, and we will require addition of z1 and z2 here. So we first write down z1 plus z2 also. To add two complex numbers we add their real parts, that is x1 plus x2 plus I times imaginary parts y1 plus y2, and we will remember this definition that if z is x plus iy, then e raised to z is given by e raised to real part of z into cosine of imaginary part plus I sin of imaginary part. This we will use here. This is the definition of complex exponential function. So now we start with right hand side, and we will prove that multiplication of e raised to z1 and e raised to z2 is e raised to z1 plus z2. So we consider this e raised to z1 times e raised to z2. Now z1 is x1 plus I y1. So using this definition, e raised to z1 will be e raised to x1, that is real part of z1, and here we will write cosine of y1 plus I sin y1. We are using definition of complex exponential function, which is if z is x plus iy, then e raised to z is e raised to real part of z, and here we write imaginary part of z. Here z1 is x1 plus iy1, therefore e raised to z1 is e raised to real part of z1, that is x1, and imaginary part is here cos y1 plus I sin y1. Similarly, e raised to z2 will be e raised to x2, that is real part of z2, imaginary part of z2 is y2. So here we consider angle as y2, cosine of y2 plus I sin y2. So this we have written using definition of complex exponential function. Now we can see that this e raised to x1 and e raised to x2 are real exponential, so we can combine them. First we write them together, and we consider multiplication of these two, cos y1 plus I sin y1, that we will multiply with cos y2 plus I sin y2, and to multiply these two we will use the definition of product of two complex numbers, and because these two are real exponential, we can use the property of real exponential, which is e raised to x1 plus x2 can be written as e raised to x1 into e raised to x2. So here x1 and x2 are real numbers or real variables, therefore e raised to x1 and e raised to x2 are real exponential functions, therefore we can write this. Now to multiply these two, we recall the definition of product of two complex numbers. Suppose we want to multiply two complex numbers, say z1 equal to x1 plus I y1 and z2 equal to x2 plus I y2, then z1 into z2 is given by a real part of z1 into real part of z2 minus imaginary part of z1 into imaginary part of z2 plus I times, here I consider real part of z1 that I multiply with imaginary part of z2, that is x1 plus x1 into y2, and then real part of z2 multiplied with imaginary part of z1, that is x2 into y1. So using this definition of product of two complex numbers, we can find out product of these two brackets. So now I am writing first, let me write another bracket here. First I will multiply real parts. So here real part is cos y1, here real part is cos y2, and minus sign is from the formula. Then imaginary part into imaginary part, here imaginary part is sin y1, here imaginary part is sin y2 plus I times, now we will consider real into imaginary. If I consider cos y1 here, I will consider sin y2 imaginary part with the real part, cos y1 into sin y2, that is real part of first into imaginary part of second, plus real part of second multiplied with imaginary part of first. So cosine of y2 into sin y1. So here using definition of product of two complex numbers, we get this. Now we try to simplify this. This we keep as it is, e raised to x1 plus x2, and if you observe, this is familiar trigonometric formula. If you can understand, this is nothing but cosine of y1 plus y2. We know that cosine of y1 plus y2 is cosine of y1 times cosine of y2 minus sin y1 into sin y2. Similarly, this second is formula of sin of y1 plus y2. We know that sin of y1 plus y2 is given by sin y1 into cos y2 plus cos y1 into sin y2. So using those trigonometric formulas, we obtain this step. Now if you observe carefully, this is nothing but e raised to z1 plus z2, because real part of z1 plus z2 is x1 plus x2 here, and imaginary part of z1 plus z2 is y1 plus y2. So using this definition, if we have z equal to x plus iy, e raised to z is e raised to real part of z, and here we use imaginary part of z. Here real part of z1 plus z2 is x1 plus x2, so that is here e raised to x1 plus x2, and imaginary part of z1 plus z2 is used here. Therefore, by definition of exponential function, we can rewrite this as e raised to z1 plus z2. So we started with e raised to z1 times z2, and that turns out to be e raised to z1 plus z2, and z1 and z2 are arbitrary real complex variables. Therefore, this is true for all z1 and z2 in the complex plane or in the set of complex numbers. So complex exponential function also satisfies this property, which is similar to the real exponential function, and it is very easy to prove this property. We have just used the definition of exponential function, and we have used the definition of product of two complex numbers. So here we stop, and we will continue with properties of exponential function in upcoming lectures. Thanks for watching.